Welcome to the first lecture. So my plan today is to do a brief review of calculus. I always think it's a bit dangerous when you start a new math class and the first thing you do is you try and review everything you've ever seen before in math. If you do that, the risk is you never actually get anywhere. So I'm going to try hard not to do that. I'm going to go quite quickly. But I do want to say a bunch of things about calculus which you should have seen in your first course in calculus, but maybe you've forgotten. At least this will refresh your memory of a bunch of techniques which I'm kind of assuming you're familiar with. I think fairly quickly I'll be doing things that you're less familiar with, but still it's going to be a very brief review. So it all starts with the idea of derivatives. So you start with some function f of x, and then you construct this new function f prime of x, the derivative of f of x. So that's the new function whose value at x is the slope of the tangent line to the original graph. So here's the picture that I'm quite sure would have been drawn for you the first time you saw this. You have some graph, x, y, so y is always short for f of x in this game, and you've got some nice curve, there it is. That's the graph of that function, and you're looking at some point, like right there. So that would be the point x, comma, f of x. So there we are, that's x. And that's f of x. And let me see, the tangent line, that's the straight line which exactly kind of kisses the curve. It just touches it exactly at that point. So here's my tangent line. Let's just make it exactly touch. There we go. So there's the tangent line. And the slope of that line, that's the number f prime of x. Of course, as x varies, the tangent line varies, that slope varies. So f prime of x is a new function. Okay. I guess when you see this, there's a little bit of an issue, because actually making sense of tangent line is a little bit tricky. To make sense of a straight line, you really need two different points. So the way you think about this is, we just have one given point on the curve. So what you do is you take some other point nearby, and so those 2 points you can join up with a straight line, and you can calculate the slope of that line. So that line is called a secant line. So it's the point you're interested in, and then some nearby point. Let's say that nearby point is, what about it? It's probably, it's a little bit more than x. So it's x plus some little change in x, which I'm going to denote delta x, and then the y value is f of x plus delta x. Okay, so if I were to draw a little right angle triangle here, there we go. It's meant to be a right angle. It might not look exactly like it. And of course, you're meant to remember that slope is rise over run. So to calculate the slope of that secant line, you need to calculate the rise. So you need the difference in the y coordinates of your 2 points. So that's, let me see, that's the y coordinate of the second point minus the y coordinate of the first point, and then you need the difference in the x coordinates. So that's x plus delta x minus x, so that's just this delta x. So delta x is the change in the x coordinate. So that's the slope of the secant line, and then the idea to actually rigorously define tangent line is you think what happens when that second point moves in towards the first point along the curve. So as that second point gets closer and closer, that secant line gets closer and closer to the thing you're going to define as the tangent line. And so that way of thinking, which I'm sure was explained to you, leads to the formula for derivative. So you have to take the limit of the secant lines to get the tangent line. The slope of the tangent line is the limit of the slopes of the secant lines, as that delta x, that's that distance right there, right? How far the new point is from the original point as that delta x approaches 0, and then it's the rise over the run. And so that becomes your definition of the derivative, that limit. And so you would have talked a lot in your first course from calculus about limits and properties of limits and got good at computing them. So there's our derivative. And while we've got it here, we should just say that there's two notations here. There's the Newton notation, which I'm using at the moment. So where you write f prime of x for your derivative. But often we'll use the Leibniz notation, where you don't write f of x, you write y everywhere, and you don't write f prime of x, you write dy by dx. And so I guess the idea of this is, well, you see, this f of x plus delta x, it would be reasonable to call that y plus delta y. And so this length here, that's the change in x. And this length here would be the change in y, delta y, in that little right angle triangle. And so our slope is delta y over delta x. And so you see this derivative, according to this definition, is the limit as delta x goes to 0. So this thing in the numerator, that's y plus delta y, that's that guy, minus y, that's that guy. Oh, so that's just delta y. And so another way of writing this is the limit as delta x goes to 0, delta y over delta x. And that's the whole idea of the Leibniz notation. It's kind of very natural. Somehow dy and dx, you're meant to think of them as these small changes, delta y and delta x, as in the limit as they go to 0. Now, of course, in the limit, delta x and delta y by themselves, those changes in x and y, become 0. So it doesn't make sense to write dy and dx by themselves, but it does still make sense to write that ratio dy over dx. That's the idea of the Leibniz notation. It's kind of a very natural way. Dy over dx is the limit of delta y over delta x. But these dy's and dx's in this Leibniz notation, they really don't make sense by themselves. So this is a whole unit. It's just one shorthand for the derivative. Okay, great. So that was the idea of derivative. So there was our tangent line. We've just calculated that thing. And let me see. I want to do one more thing on this picture. My picture's getting a little bit cluttered, but let me try and take our tangent line and let's make it into a right angle triangle as well. There we are. And I want to just say something about that angle there. So that angle theta. So theta is the angle of the tangent line to the horizontal. Always when you measure angles, you measure them counterclockwise like that. So that's a positive angle that I've drawn there. And so the observation I wanted to make at the end is that tan theta, well, what's tan theta in a right angle triangle? Tangent by SOHCAHTOA.
Opposite over adjacent. So tangent, it's the rise, the change in y, over the run, the change in x.
So tan theta is exactly the derivative. Right, so the slope of the tangent line is the tangent of that angle. So I guess the use of the word tangent makes a little bit of sense there. Okay, so that's a useful little formula. I just thought I'd write it down for later on. Okay, fantastic. So let me see, let's carry on. So in your first course on calculus, I'm quite sure that you spent quite a long time using derivatives to find what are called critical points. Functions. So a critical point, that's a place where the derivative is 0. So the tangent line at that point is horizontal. And of course, that happens at the peaks and the valleys of your curve, of your graph. And so once you can find the critical points, you can find the maxima and the minima of your function. So I'm quite sure you would have spent a lot of time taking kind of various word problems and constructing functions out of them, finding the critical points, and therefore maximizing, minimizing, solving optimization problems about those functions. And it all works because the derivatives of all the kind of elementary functions that you've come across are very easy to calculate. This theory would be useless if this thing we called the derivative, defined by that crazy looking limit, if you couldn't actually compute it. But the whole point is it's eminently computable. And so you can take a whole bunch of functions and you can quickly find the derivative, find the critical points, maximize, minimize those functions. So I want to talk a little bit about some of the tools to differentiate, which makes all those derivatives easy to calculate. I guess the most basic of all is the power rule. So we should start there. Let me remind you of the power rule. So that says that the derivative of x to the n, okay, so this is the first time I've used d by dx by itself. D by dx, this is Leibnizian notation, that's the instruction to differentiate with respect to the variable x. So what I'm saying here is that the derivative of the function f of x equals x to the n, f prime of x is, so here's the power rule, nx to the n minus 1. So this is super important, and I have a little mantra that goes on in my head whenever I do the power rule. It's power down the front, 1 off the power. I'm quite sure you would have spent lots of time applying that rule in practice. Let's just think about how that was proved, because you see the proof goes back to the definition of derivative. The definition, it's the limit as, well, let me not write delta x, let me write h, because that's also often used. So instead of writing delta x goes to 0, I'm going to have h goes to 0. It's a little easier to write. And then what was it? It was the function at x plus delta x, so the function at x plus h now, so there's our function, minus the function at x all over, it was delta x before, but I'm just writing h. Okay, so that's the limit we've got to calculate. And so to calculate this limit, okay, so I'm only proving this when n is a natural number. The power rule is true for any constant power, not just positive integers, all integers, all rational numbers, all irrational numbers, any real number up there. You can have like the number pi or anything like that. You bring the power down the front, pi x to the power pi minus 1. That's what it would be if it was x to the power pi. Okay, so it's any constant power. And I'm just writing out the proof in a rather lame special case when the power is just a positive integer. And the point is, when the power is just a positive integer, I can expand that bracket x plus h to the n. I can multiply it out by using the binomial theorem. I'm not going to review the binomial theorem in a whole lot of detail. That's the thing that involves Pascal's triangle, which I'm sure that you've seen. So this is called a binomial, and you can expand it. And the coefficients that show up are the coefficients on the nth row of Pascal's triangle that I've got there. Okay, so heck, I'm just going to do it. When n is 3, let's make life really easy for ourselves. So I'm just doing it when the power's 3. Okay, so I'm just doing, but doing it for the power 3, this is the same as doing it for any natural number if you know the binomial theorem. So the limit we've got to calculate is x plus h cubed, and by the binomial theorem, when you multiply that out, you get x cubed plus 3x squared h plus 3xh squared plus h cubed. So that's what the binomial expansion of that cube is there. And then I still got the minus x cubed, and I'm over h. Okay, so that's the binomial theorem for the power 3, and you see the coefficients 1, 3, 3, 1. They're the coefficients in that row of Pascal's triangle. Okay, and so now I can, let me see, that x cubed and that x cubed cancel, and then I can divide through by h now, because every term that's left has got some h's in it, so I can cancel the h on the denominator. I get, what, 3x squared plus 3xh plus h squared. And now I can calculate that limit. As h goes to 0, that term goes to 0, and that term goes to 0. So we just get left with 3x squared. And that's what we were expecting if you were differentiating x cubed. Power down the front gives you 3, 1 off the power, 3x squared. Okay, so I kind of cheated and just proved it for x cubed, but that same argument using the binomial theorem will prove it for any positive integer power. It's not much harder to prove it for negative integers or even for rational powers, but it gets pretty difficult to prove it for powers that are constants but not rational numbers, like pi or something like that. Power down the front, 1 off the power. How to prove that is more of a challenge. That the challenge really is working out what x to the power pi really mean. It's really non-trivial. It's easy to everyone knows what you mean by x cubed. You mean x times x times x. Or negative powers, you mean 1 over the positive power. Rational powers, like to the half, is square root, and so on. So those are easy to define, but making sense of what x to the power pi is an irrational number, even means, is kind of difficult. And so proving the power rule for such powers is a bit tricky, and I'm going to talk about it a little bit later on. All right, so that's the power rule, which I'm quite sure you applied many times. So here are some other tools. There's the product rule. There's the quotient rule. And then last but most important and kind of most difficult to understand, because it comes in many different forms, is the chain rule. So I'm just going to quickly remind you of these. I'm quite sure you've seen these before. So the product rule tells you how to differentiate f times g, a product of two functions. So that's the new function, f times g, whose value at x is the number f of x times the number g of x. And the product rule tells you that the derivative of f times g, it's f prime times g plus f times g prime. So when I say the product rule, I call f the first, and I call g the second, and then it's the derivative of the first times the second plus the first times the derivative of the second. That's the little rhyme that I have going in my head whenever I do the product rule. Let me see. Let me write that. So the product rule is also known as the Leibniz rule, by the way. And I want to write it in Leibniz notation as well. So what I've written so far would be the Newton way of writing the product rule. The Leibniz way would be d by dx of u times v. So u would stand for f, and v would stand for g. And you want to differentiate the product uv with respect to x. So in Leibniz notation, so u is the first, v is the second. It's the derivative of the first times the second plus the first times the derivative of the second. So there's product rule. I'm sure you used that. Let's quickly do quotient rule, so that's not f times g, but f divided by g. And so when I say this one, the f is the top and the g is the bottom. And so the quotient rule, it's bottom times derivative of the top minus top times derivative of the bottom all over the bottom squared. Or in more Leibnizy notation, it's the derivative of u divided by v, bottom derivative of the top minus top derivative of the bottom all over the bottom squared. Okay, so that's something I'm quite sure you used the quotient rule. I'll do an example a little bit later today, just to remind you. Remember, that's all I'm trying to do is just refresh your memories about things you've definitely seen, so that when I start using them in our applications, when we're actually doing useful things with calculus in a little while, you won't be totally thrown. So the final one is the chain rule. And as I said, this is kind of the hardest one of these rules. So this is to do with f composed with g. So f composed with g, that's the new function whose value at x is f of g of x. So when I just say, I call this f after g. Okay, so you take your x, you feed it into the function g, and then you take the output of the function g and you feed that into the function f after g. So when I'm thinking about this one, I call the f, I call it the outside function, and I call the g the inside function, because in this notation, look, f is outside the brackets and g is inside the brackets. And then the chain rule tells you how to differentiate f after g, and it says it's the derivative of the outside evaluated at the inside times the derivative of the inside. Let me start writing it in a slightly different way. Another way of writing the same thing, I could be a little bit more Leibnizy. So it's f of g of x. To differentiate that with respect to x, it's the derivative of the outside evaluated at the inside times the derivative of the inside. Or even better, if I call this thing here u and that thing there, v was short for g of x, then I could just write it in one go. It's du by dx, that's the left-hand side. And then this, so this is going to be du, that's f prime, f is u, so that's du by dv. So that would be du by dv, and then this term here, this is dv by dx. Right? And so this is the place where you start becoming convinced that this Leibniz notation is very handy, because the chain rule looks so nice in Leibniz notation. Look at that, that looks beautiful. And it's very easy to remember, because although this is not a fraction, it's a single unit, you can't treat the du and the dv as being separate. This chain rule, it's just the same as the rule for multiplying fractions. It's as though those two guys are cancelling, leaving the fraction du by dx. So that's sort of the first place where you start seeing this Leibniz notation is kind of handy. Okay, so quick review of differential calculus, that's what's going on. I want to make sure that you know about some of the basic functions. Let's talk about exponential and logarithm functions. So that's the function e to the x and the function natural log of x. And I'm sure you know that these are inverse functions. So that means if you start at x and you feed it into the exponential function to get e to the x, and then you take natural log eats e to the power, and it leaves you with the x you started with. Or if you start with x and you feed it into natural log, and then you do e to the power eats natural log, and that gives you x back again. Yes, so that's what it means to say that they're inverse functions. I'm not trying to teach you what these things are. I'm just trying to give a quick review of things that you know, but let's at least draw the graphs of these functions. So here's the graph of e to the x, here's the graph of natural log x. So the exponential graph looks a bit like that. That's 1. And then, because natural log is the inverse function, all I have to do to graph that is flip in the line y equals x. So when I flip that graph in the line y equals x, I get that. That's the graph of natural log. What to say next? Let me see. We should talk about derivatives. I just want to remind you, the exponential function is the world's easiest function to differentiate. The derivative of e to the power x is just e to the power x back again. And the derivative of natural log x, derivative of natural log is 1 over. Okay, so those I'm going to assume that you know those. So let's put little boxes around them. There we go. There's something going on here. We're using this number e, 2.718, whatever it is, this crazy irrational number. Why is that used as the base for exponents? Why is that the right thing to do? Well, the thing is that if you look at the tangent line to the exponential graph where it crosses the y-axis, so there's that tangent line. So the slope there, well, slope, that's the derivative, so it's the derivative when x is 0. The derivative is e to the x. When you plug in 0, you get e to the 0. So the slope of that line is e to the 0, which is 1. You pick e as the base for exponential functions so that that slope of that line is exactly 1. And then that's basically the same as this property that the differential of e to the x is just e to the x. It's really important. That's where this number e comes from. That's its key property. If you had done something maybe a little rash, but you probably did this the first time, you saw exponential function and used 10 as your base, that seems rather natural, then that wouldn't work out. The derivative of 10 to the x is not 10 to the x. Let's calculate that actually. How do you differentiate 10 to the power x? Well, 10 is e to the natural log of 10. Okay, so I've just written the number 10 again in those brackets. We want 10 to the x, so we want that to the power x. So we're trying to differentiate e to the natural, I'm just using laws of exponents, raising to a power, you just multiply the two powers. And now I can differentiate using the chain rule. The outside function is the e to the power, and the inside function is this scalar, natural log 10 times x. So I can differentiate the outside evaluated at the inside, and then the derivative of the inside, this is just a scalar times x, so its derivative is just the scalar. And so finally that's natural log of 10 times e to the ln 10x. We already saw that's 10 to the power x. So when you differentiate 10 to the x, you don't get 10 to the x back again. You get scaled by natural log of 10. That would be the slope of the tangent line when it crosses the y-axis for the graph y equals 10 to the x. You see, and that's really inconvenient. You need to use e to get this most memorable formula, the easiest possible derivative. Let's do one more example. Let's do x to the pi. I mentioned that earlier, but I'm writing pi because it's my favorite irrational number, but I could take x to any real number power here. So now I can tell you what that means. X to the pi means, well, let me be a little bit circular. So x, it's e to the ln x, because x, e to the power, and ln are inverses, and we want to raise it to the power of pi, right? And then by laws of exponents, well, that's e to the, multiply the exponents, pi times ln x. So actually that's the definition of what x to the power pi means. It's e to the power pi ln x. And so what you have to do is define the exponential function. Once you've defined e to the x, somehow you've defined all other to the power functions. And I'm not quite telling you how to do that. I might do that later on in the course. So I'm being a little bit mean here. But remember, I'm just trying to review things. So x to the power pi just means e to the power pi ln x. And so now I can differentiate x to the pi, because what it means is e to the pi ln x. And I can differentiate that using the chain rule. It's the derivative of the outside function, evaluated at the inside, times the derivative of the inside function. This is the inside function. Its derivative is pi over x. So what have we got? That's pi over x times x to the pi, which is pi. So now I've got an x to the pi here, and I've got a 1 over x, which is an x to the power minus 1. And then if I add those exponents, it becomes x to the pi minus 1. And so you see it is indeed power down the front, 1 off the power. That's all I want to say right now about exp and log. I've hopefully reminded you of a few facts about those functions. Then the last thing I want to do today is say a little bit about trigonometry, about trig functions. They're going to be very important for us as we move forward, because we're going to be doing a lot of physics and describing how things move, and trig functions come up all the time when you're doing that sort of elementary physics, which we're going to see. Okay, so trig functions. It all starts with sine and cosine, which you learnt in elementary geometry. You probably had a right-angled triangle, and that would have been the angle x. Let's say the hypotenuse is 1, and so you learn this SOHCAHTOA rule. Cosine is the adjacent over hypotenuse. So this adjacent side must be cos x, because cos x is adjacent over hypotenuse, and sine is opposite over hypotenuse, so this opposite side must be sine x. Okay, so that's kind of the elementary way of talking about trig functions, which is good enough for now. And the other classical thing from geometry is Pythagoras, which tells you that the sum of the squares of the short sides is the square of the long side. So in this right-angled triangle, that tells you that cos squared x plus sine squared x equals 1. So that's, I guess, the very first trig identity that everybody should know and use all the time. So that's sine and cosine. And then there's lots more trig functions. I guess that's why trig is kind of a difficult subject. There seem to be a bewildering number of functions. There's tangent and secant, and there's cotangent and cosecant. And I always think that these things really go in families. Sine goes with cosine, tangent goes with secant, and cotangent goes with cosecant. So let me see, what are these? Tangent, by SOHCAHTOA, tan x, it's opposite over adjacent. So that's the definition of tan x. It's just short for sine x over cos x. And in cotangent x, that's 1 over tangent x. So that's cos x over sine x. And then the secant begins with s. It's 1 over cos, the other letter, c. And cosecant begins with c. It's 1 over sine, the other letter, s here. Okay, so these this sort of historical, kind of archaic-looking names for these trig functions, which I think is always rather charming. So there they are: sine, cos, tangent, secant, cotangent, cosecant. And I said they go in families. Sine goes with cosine, tangent goes with secant, cotangent goes with cosecant. Let me just explain why they go in families. If I take Pythagoras right here, that's cosine and sine appearing in the same formula. If I divide both sides by cos squared, I get 1 plus sine squared over cos squared, which is tan squared, is 1 over cos squared, which is sec squared. So that's tangent and secant in that version of Pythagoras. Tangent and secant appear in the same Pythagoras identity. Or I could take the original Pythagoras and divide both sides by sine squared. So then I would get cos squared over sine squared, which is cot squared, plus 1 is 1 over sine squared, which is cosecant squared x. So that's the third flavor of Pythagoras, which involves cotangent, cosecant, that third family of trig functions. So these are your most basic trig identities. We'll come across lots of other trig identities as we're going, because you need them, but these are the three kind of fundamental ones at the very beginning. Okay, great. So let me see, I've already been using this notation sine squared x, because I think everybody is familiar with that, because that means sine x squared, it's just short for that, which is sine x times sine x. And if you by that notation, then when you write sine inverse x, I always think you should mean sine x to the power minus 1, which is of course 1 over sine x. And that's how I use the notation. That's what I mean when I write sine inverse x. So this is definitely not the inverse trig function. Many calculators, many people, when they write sine inverse, they mean the inverse trig function. They do not mean 1 over sine. But I think it's better to have the convention that sine inverse means 1 over sine, and then you need a different name for the inverse trig function, and I use arcsine x for that. Right, so arcsine is the inverse function to sine. Similarly, there's arccosine and arctangent. Those are the inverse functions to the cosine and the tangent functions. So I want to just talk a little bit about those guys. Let me just stick to arcsine. I think that's enough in this brief review. So if y is arcsine x, if you apply sine to both sides, you get sine y is sine of arcsine of x. And sine and arcsine are inverse functions, so they cancel each other out, and you just get that sine y equals x. Okay, so that's the idea. That's what arcsine is. Let's maybe draw a little bit of a graph. I'm going to try. I'm not very good at drawing graphs. Let's see how I do. So this is up at y equals 1, and this is y equals minus 1. And then let me try and draw sine, so it goes kind of nice and curvy, and curvy. It's not too bad, not great, because I'm not very artistic. So this is the graph of sine x. And this point up here, that's at pi by 2. And then that's pi, and that's 3 pi by 2, and that's 2 pi. This graph is periodic with period 2 pi, so every 2 pi it just starts repeating. Let's move that up a little bit so I have a little bit more room. So the thing about this function is that it's not one-to-one. There are lots of different inputs that have the same output as one, as another input. All those inputs have the same output. So this function is not one-to-one. And so it actually doesn't have an inverse function. You need your function to be one-to-one before you can talk about the inverse function. So what do I mean when I say arcsine is the inverse function to sine? Well, what you have to do is you have to narrow in the domain. So that would be, right there is minus pi over 2. So you need to restrict the domain. sine to just the interval minus pi over 2, pi over 2. And on that restricted domain, so we're just looking at this piece of the graph, on that restricted domain, the function is 1 to 1. Arc sine is the inverse function on that domain. Okay, so this is sort of a kind of awkward thing. I could plot the graph of arc sine. Let me do that. So to plot the graph, you just reflect in the line y equals x. So we're just looking at this little piece of the graph. So it goes up and then through there and then down. So this would be 1, and that's minus 1, and that's minus pi over 2, and that's pi over 2. That's the graph of arc sine. So arc sine, it takes input between minus 1 and 1, and it spits out an output, an angle that's always between minus pi over 2 and pi over 2. And I guess this is one of the places where trigonometry gets a bit confusing. If you know the sine of an angle, you don't actually know the angle uniquely. If you hit the arc sine button on your calculator, it gives you the angle between minus pi over 2 and pi over 2 with that sign. But you need to know more about the angle you started with. You might need to add on some 2 pi's or 2 pi minus or something like that to actually find the actual angle from what your calculator tells you. There's a similar story for arc cosine and for arc tangent. I'm not going to say those things, but let me just really quickly draw the graphs. So here's just a really quick sketch. So this is arc cosine, and this is arc tangent. So arc cosine, the graph looks like this, where again this is 1, and that's minus 1, and this time this is pi. And arc tangent is particularly nice. It has 2 horizontal asymptotes at pi over 2 and minus pi over 2, and the graph looks something like this with those asymptotes appearing. So that kind of gives you just enough information to piece together how you restrict the domain of cosine and tangent before you take inverse functions to get arc cosine and arc tangent. But I'm not going to go through that in much detail. What is crucial to point out here is that when you do trigonometry and calculus at the same time, you must always use radians. So when I write sine, I mean the sine function for x in radians. Always. And the reason for this is similar to the reason why you need to use e as the base for your exponents. If you take the sine curve and you draw the tangent line through where it crosses the y-axis, so this tangent line, let's see if I can sort this out, this tangent line it has slope 1. You want that. That's why you use radians. It makes that tangent line through the origin exactly have slope 1. And the consequence of that is that of that choice is that the derivative of sine is cosine, and the derivative of cosine is minus sine. So it's absolutely crucial that you use radians for these derivatives to be so nice and to work out so neatly. So let me see, I just want to finish off with a couple more examples. Let's just think about the derivative of tangent. So how would you do the derivative of tangent? So tangent is sine over cos. So I could use the quotient rule. It's the bottom times the derivative of the top. The top is sine, so its derivative is cosine, minus the top times the derivative of the bottom. The bottom is cosine, so its derivative is minus sine, so that minus sign switched to a plus sign, all over the bottom squared. And now on the numerator I've got cos squared plus sine squared, which is 1 by Pythagoras, so I've got 1 over cos squared, but you should use secant because you're talking about tangent, so you want to stay in the tangent secant family. The derivative of tan x is secant squared x. Let me just write down the derivative of secant x. That's secant x times tangent x, and you can prove that for yourself. Let's just do one more example. Let's calculate the derivative of arcsine x. It's just the very last thing I'm going to do here. So when you're doing this, you have to be a little bit devious. You have to let y equal arcsine x. So what we want is dy by dx. But if y equals arcsine x, that's the same as saying that sine y equals x. And then you can differentiate both sides with respect to x. D by dx sine y is d by dx of x. Now the right hand side is easy, right? D by dx of x is just 1. But the left-hand side, to calculate this, is a little bit harder because, well, that's an x, whereas we know the y is here. So you have to use the chain rule. You have to write that d by dx as d by dy of sine y times dy by dx. Remember the chain rule? It's as though those dy's cancel and they leave d by dx at the end. So that's the use of the chain rule, a sneaky one. And then from there I get, let me see, I get that dy by dx, now d by dy of sine y is cos y, is 1. Therefore, dy by dx, the thing we want, is 1 over cos y. But of course we want the answer in terms of x. And we know sine y is x. So we've got to replace that cos y by sine y's, which we can do using Pythagoras. 1 minus sine squared y. Cos squared is 1 minus sine squared. And so and then sine y is x, so that's 1 over root 1 minus x squared. So we've just worked out that the derivative is 1 over root 1 minus x squared. You could calculate the derivative of arctan at this point by a similar method. The derivative of arctan x is 1 over 1 plus x squared. So let's just put some little boxes around all the formulas that we've proved, all the derivatives for trig functions. Derivative of tangent is secant squared. Derivative of secant is secant tangent. Derivative of arcsine is 1 over root 1 minus x squared. Derivative of arctan is 1 over 1 plus x squared. Okay, so that's where I want to stop. I've reviewed actually a lot of stuff fairly quickly today. In the next lecture, I'm going to start talking a little bit about differential equations, equations involving derivatives, and laws of motion. And we'll start doing a little bit of beginning physics, because, of course, that's what calculus was invented to do.